Hello, everybody. I'm Tova, Tova Milo from Tel Aviv University, and I'll be giving this invited talk on getting rid of data. Okay, so let's get to business. What is it, this getting rid of data thing that I want to discuss today? Well, it's known that our world is flooded with information, and we're using data practically for everything. You know, from analyzing sport events to deriving new healthcare plans and so on. It all depends on data that is being collected, and really this data-centered revolution that we're experiencing is really fueled by the masses of data that we're obtaining. But the thing is that a lot of information is great, but too much is too much, and we really risk something that is called information flood. Now, let's be careful in explaining what exactly I mean by information flood. So people have been discussing the too much information thing for several years now, but in a sense, what bothered them was that with these tons of information, it's really hard to find or extract the things that are of interest to us. So this is really a performance problem, or the design of better analysis tools problem. But this is not what I want to talk about. I really want to talk about the fact that actually collecting and keeping all this data is not necessarily a good thing, and we have to rethink this more and more data philosophy, and actually have to start getting rid of data practically. And I will talk, I'll try to convince you that this is the case. And for that, I want to point at three aspects of this too much data thing. The first is related to production rate, how much data we are generating, and compared to how much storage we have. The second thing is really related to performance, like what I mentioned before. And the last thing is related to privacy of information. So let's start. So first of all, let's think about how much data do we actually generate. And it turns out that there are quite a few surveys and papers that discuss the amount of information that we generate. And what's interesting is really that the numbers, the predictions on how much data we will generate grow every year. For instance, in 2017, it was estimated that by 2025, we will grow to 163 zettabytes of data generation. 1 year later, the estimate was already updated to 175 zettabytes. This is a lot. But the fact that that's a lot, it's not so bad. What's the problem with that is that this is really far more than how much we can store, how much storage is generated, and the production rate of storage are much slower. So let's try to visualize just a little bit. So this is more or less how the data generation curve looks like, and as you can see, currently we're somewhere here, and we're going to grow up to here. So I think we all realize that 175 zettabytes of storage is a lot, but let's try to visualize this a little bit. So suppose you take all this information and store it on the Blu-ray disc, like the standard disc, and you put them one on top of the other. So practically, this will allow you to get to the moon 23 times. That's a lot, right? Or alternatively, if you download all this data on today's hard drives, it will take 12.5 billion drives to store all this information. We don't have that many drives in the world. So if you actually look at how many drives or how much storage we actually have or will be producing in the next few years, so this is how the curve looks like. Today we're somewhere here, okay, and in 2025 we'll be here, okay. So let's put these two graphs one on top of the other. So this is how much storage will be generated, 5 zettabytes, and this is how much data will be generated, 175 zettabytes. There is a lot of gap between these two things, and what are we going to do with all this information that is generated and cannot be stored anywhere, okay? But even if you forget storage, you say, okay, I'm a rich company, I'm Google or Twitter or whatever, I'm very, very rich, I'm gonna buy all the storage in the world, all the other people, I'll leave them without storage, but for me, I will have everything that I need. Still, you have to think a bit harder, because too much data is not just a matter of storage, it's also a matter of performance. You have tons of data, you need to clean it, you need to validate it, you need to enhance it, you need to analyze it. And this is really a performance bottleneck. And to improve performance, really, you have to be far more selective, okay? So performance is something that we database people are kind of used to think about, but I want to discuss a different angle of performance, which is really energy consumption, okay? If you think about all the data centers where we store all this data and analyze it and so on. So again, there is an estimation that by 2025, just the data centers that where we put all the information will take 20% of the Earth power. Okay, this is a lot of energy. And the thing is, okay, you can think, okay, this is kind of a pessimist evaluation. Maybe things will not get so bad, but you can really look at today, okay? In 2014, data centers consumed 1.62% of the world's energy. A year or two later, this has already increased to 3% of the world's energy. And if you think about it, if you want to visualize it, you want to compare it to something else, this is how much the whole travel or airplane industry is consuming today, okay? And there are a lot of efforts, right? People are telling us don't fly so much because it's bad for the world and so on. Nobody tells us, okay, store less data because that's bad for the world, right? But in terms of energy, already today, we're doing as much damage as airplanes flying all over the world. And in terms of these data centers and the energy that they consume. So there has been quite a bit of work over the last few years to decrease the amount of energy that the data centers are consuming and really optimize the processing. They designed different better ways to cool the data centers, to recycle the heat of the wasted heat, to do all sorts of switching to renewable energy. Still, if you look at the researchers on this area, they predict that even in the best scenario predictions, okay, if we don't learn how to dispense of the data and kind of not expand what we have too much, we'll stay with the same consumption level, which is already very high, okay? Okay, maybe you don't care about the energy, you don't care about the world getting warmer or whatever. Still, there are other reasons to worry about this storage of too much data. And this is the third P, it's the privacy and security, okay? So already now we know that all these companies are storing a lot of information which is sensitive, okay? About us, about what we're doing, about what companies are doing, and so on. And the fact that people store information has two sides. Okay, first, we may not want them to keep it, and second, a company that stores information has to be reliable and has to provide guarantees about for the information that it stores. And really, there are all these regulations that are starting now, like the GDPR in Europe, but also other standards for keeping information. And again, for a company to guarantee that all these regulations are kept, it takes a lot of energy, takes a lot of work and overhead and so on. So it's really important that companies systematically develop and enforce data disposal and retention policies. Okay. So I hope that I convinced you that not keeping all the information, getting rid of some of it is important. And we'll soon start talking about how to do that, what people have been doing, and so on. But before that, I want to point out 4 important things. The first one, which is kind of obvious for all of us, really, not all this data is important, right? We collect tons of garbage, and every person, if you look at your laptop, if you look at your cell phone or company, if you look at your repositories, there's tons of information which obviously we don't need. Okay, so really getting rid of data is not something that is inconceivable. And if you look at the graphs that people have been constructing to kind of grasp or capture how much information from what we keep is important and how much is not. So you look at these 3 categories of data that is hyper important, important, or potentially useful. So even if you just look at what might be potentially useful at 2025, it's only around 65 zettabytes out of these 175 zettabytes that I showed you before. So really, it's less than half. Okay, so half you can trash. And even for the rest, there's tons of it, which is, okay, maybe you will need it, but very unlikely you can get rid of that. So yeah, we don't need all this information, but still, it's really scary if you think about it, to delete a file. Okay, you look at your repository, there is this file that you have no idea what it contains. You absolutely don't need it, but it's really stressful to press delete. So people really fear of losing information that maybe 2 years from now they will realize that too bad we deleted it. So really, if you really fear about that, still you can do something. You don't have to keep it active on a disk. You can put it on a tape on the side, and that's fine. One day, if you will need it, you will go and get it. But for now, at least for your operational database, you really don't need it. So at least, even if you don't want to delete things physically, you need to separate. Okay, put on the side the stuff that is unlikely to be used, and in the worst case, you will go there, you will mount the disk on, and it will take you a little bit time to restore it, but it will not disturb your operational development every day. Okay. The third thing to understand is that sometimes you really don't have a choice. Okay, if your storage is limited, or if your energy is limited, if your resources are limited, you have no choice. So it's true, maybe at some point in the future, you will need the data, but if you don't have a choice, you have to delete it. Okay, and it's better to have a reasonable, smart policy than just delete things randomly in a nonsensible way. So you have to, we have as a community to design good strategies for getting rid of data. And the last thing, which is very important to point out, that I'm not the first one to point this issue. Actually, 5 years ago in Cider, there was a really cool talk by Martin Kirsten, that actually got the Wildest Idea Award, and he was talking really about exactly the same things, about the fact that all these data spaces that we have contain tons of junk which we should get rid of. And to my so I think that this didn't get the attention that it should have gotten, just because, like many good ideas, it was too early. Okay, there was not really a problem of too much data then. Okay, but now as time advances and we collect more and more and more information, we're really at the point where we should start worrying about it and do something about it. So I hope that by now I convinced you that there is a problem and that we as a community should be looking at this problem. And now let's try to see what people have been doing or have been thinking about this thing. And keep in mind that the challenge really that need to be addressed here is that we want to determine a good disposal policy, but not just to get rid of data, but also to support the full cycle of information processing over this partial data. Okay, everything that we're doing today, from integrating data or cleaning it or analyzing or whatever, we should be able to do more or less in the same quality and effectivity as we would have done had we not deleted all this information. And also we have to keep in mind that data is coming all the time. So this has to be incrementally maintained. Okay, as we get more data, we have to think again what to delete and so on. So this is the challenge, and let's try to see what we can do about it and how we can address it. Okay. So first of all, I'd like to mention what has been done in the community so far. And once I'll start talking about it, you'll realize that almost everyone, almost each of you, have been doing something related to this problem. And actually, the challenge is to glue together all these beautiful things that people have been doing over the years and try to put them to work together to solve this big challenge. And then I'll talk a little bit about how you can use past activities to decide what data to delete and what to keep. This is related, not surprisingly, to provenance. And finally, I'll talk about predicting the future, or how to deal with new information on which you have no idea yet, how to decide what's important in it and what is not. So let's talk a little bit about existing tools. So here's the very incomplete list of tools that are relevant for this problem, how you take tons of data and you reduce its quantity. So people have been working on entity resolution, for instance, how to see the different parts of the data represent the same entity and can actually be consolidated and reduced. People have been working on compression and summarization of relational data, semi-structured data, and unstructured data. People have been working on sampling, okay, how not to look at the full data, but rather just to look at a small sample. This is related to approximate query processing. Similarly, people have been looking at sketching. This is related in particular to streaming data when the data comes and you don't want to store it, but just to sketch it. And then more recently, people are working a lot of machine learning, and there are many ways to reduce the data at hand. So people have been working on dimensionality reduction, clustering, feature selection, and so on. So I'll just give a couple of really representative examples. Don't be offended if you've been working on some of this work and I haven't mentioned you. Okay, this is really just a random sample. Okay, so already in the 90s, for instance, people have been looking at relational databases and how to compress them. So just to illustrate, suppose you have a big relation with about people with their age, salary, assets, credit, and sex. So this is a huge thing. You can reduce its size by compressing. Okay, so for instance, you can build this what people have been calling in this paper, for instance, by Jagadish Nag and Oyen Tang, a representative row. So you take a bunch of tuples, for instance, the first and the last two tuples here, and you represent them by one tuple that kind of can think about it as the average or something like that of values. And then you can keep another table that tells you how different the original tuples are from this representative tuple. So for instance, the first tuple here is almost the same as its representative tuple, except for some attributes that are different, and so on. So this is just an example of one way to compress the data. So this has been done since the 90s, and later people have been doing similar things for graphs. So again, you have a big graph and you want to represent it as a smaller thing. So you take a bunch of nodes and edges here, you represent them by a small graph here, and here you kind of explain how you map the full information to this small summary. So that's just one example of graph summarization. There are many, many others. The last type of work that I want to mention, again, just as an example, is work on sampling. So there's tons of work on sampling for approximated query processing. In principle, there are two ways that people implement in order not to look at the full data. So one line of work talks about query time. Okay, you have a query, and then in order to answer it, instead of processing the full data, you sample a little bit, and then you evaluate against the sample. Something which is more related to what we're discussing here, kind of reduction of data. And if you want a better response time, what people are doing is some sort of pre-processing. Okay, you take the data, you sample from it in advance, and then at query time, independently of what the query is, you evaluate it on the sample. If you're interested in this topic, there was a really, really nice keynote in SIGMOD 2017 by Chadhuri, Ding, and Kandula, and you can go and look at the paper. There are tons of references to work in this area. It's really cool. It gives a really nice overview of the sampling idea for database. Okay, so these are just a few examples, but if you look at all these kind of works that I've shown you before, they have really common objectives. Okay, in a way, you want the summary, okay, or the concise representation of the data not to be too big. Okay, so you will save space. You want the pieces of the summary to be diverse so that they cover in a way the information. Okay, so you want some coverage so you don't lose too much information. And then the quality of this summary information is typically computed or evaluated with respect to the query result. Okay, what you want is you want the queries when evaluated on the summarized data to be more or less the same as if you would have executed on the original data. Okay, and then you can either compare it with respect to one concrete query, or perhaps with respect to a query workload, or in general about how much information is lost. And again, I want to point a really nice paper by Orsuchu and Balazinska from ELDP 17 that really proposes a nice way to measure how much information is lost. Okay, so it looks like people have been doing tons of work on that. They know how to reduce the amount of information. So why am I arguing that this is a good research topic for us to work on, or what else is there to be doing here? So the point is that really all these works, or at least most of the ones that I'm familiar with, have been focusing on query evaluation. Okay, now in practice, what we do with the data, the workload, is far more complex. Okay, I don't know, people from from the audience that are teaching data science course are probably familiar with this diagram. It's called the crisp DM diagram that kind of describes the pipeline or the workload of people that are doing data science over information. Okay, so they're doing cleaning and transformation and integration, and then machine learning, and then starting again and doing again understanding of the data and preparing it and cleaning it better and modeling it. And so there is really a pipeline, an iterative pipeline that people are doing with the data. It's not just querying. Okay, querying is at the end. Okay, but there are tons of things that you're doing with the data, and this summarized information has to support all of them. So when we measure what's a good summary, or which data we should get rid of, we should take all this pipeline into consideration. Okay, it's not enough just to consider queries. So we need to understand how the data is manipulated, how it is summarized, and how to dispose of some of it throughout the entire workload. Okay, and how to support the workload over this data. So in order to support something like that, we first have to understand what people really are doing in the data. And I argue that provenance is a good way to do it. And let me remind you what is provenance, and give you some intuition about what we can do with it. So provenance is some annotation, okay, that is typically connected to the data, kept with the data in order to preserve some information about the source of the data. There are tons of models and so on. Let's just look at one example. So for instance, suppose you have this database, okay, that has customers and loans and some relation that says which customer took which loan. And suppose that what we're interested in is how many customers had a loan application denied in the 2017 and got accepted in 2018 per zip code. Okay, so what does it actually mean? It's not really important to understand the syntax of the SQL query that does it, but in general, what we'll do is we look at the tuples here, and we will connect them to the loans through this connection relation, and then we'll try to find here users that had a denied loan and which was approved later. So if we look at the provenance that records how this query is evaluated, we can see that Merge and BART, okay, here had no request for loans at all, and therefore they're irrelevant for the query computation. Okay, which means that if this is all that we're interested in, we can delete them. Okay, and even further, if we look at how the query is computed, so for instance, there is something which is called Provenance Polynomials that really keeps record of the information that was on how the query was computed. Again, it's not really important to understand how these polynomials are built, but in general, what they tell you that Lisa is in the result, okay? Because she had actually two loans that were denied, both the first loan and the second loan. And what it tells us in terms of data preservation is that in order to have Lisa in the result, actually we don't need the two things. Okay, we just have to know that something was, some loan was denied, so we can delete one of these two tuples. Okay, so looking at the provenance, what I want to argue is that looking at the provenance helps us to see what things are completely irrelevant for the computation, and even within the things that are relevant, to distinguish between the things that are optional and therefore can be deleted. So this is a simple example on provenance for relational data. There has been work on provenance also for workflows, which is far more complex. I'm not going to get into it, but provenance really has been used for many things in database research, for results explanation, for hypothetical reasoning, for trust level assessment, and so on. And what we've been showing in recent work is that actually it can be used for data reduction. And really using the provenance to understand what happened with the information is very important. Okay, so this sounds like a good direction for research, but actually it's not so obvious, because I was complaining that we have too much information and therefore we need to reduce it. But the thing is that the provenance itself, these polynomials or all this information that we keep, the annotations that we keep with the data in order to know what contributed to what, by itself is very, very big. Okay, so in order to reduce the data, you have to keep the provenance, but the provenance takes a lot of space, so you have to reduce it as well. So it's kind of a recursive problem. And indeed, there has been quite a bit of work on provenance reduction, how to take this big provenance and kind of summarize it and keep it in a much more concise way. And there are two ways to do it. One is lossless. Okay, you take the provenance, and instead of keeping the big provenance expression, you try to simplify the expression or to factorize and keep the same information just more compactly. And the other type of provenance reduction, like in data reduction, something which is lossy. Okay, you keep only part of the provenance which you think might be relevant for the computation that you do, or you compress it, and so on. So again, like for data reduction, there's interest in studying provenance reduction to understand better how to keep provenance effectively for keeping the data effective. Okay, so far I've been focusing on the past, actually, because I assume that, okay, I have this data, it has been already processed by people, and therefore we can look at how they process it or what they did with the data, and then from that infer what is more important, what is less important, what has been used, and so on, and reduce the data through that. Okay. The thing is that in our modern world, often we get a new set of data, which, you know, we haven't seen it before, we haven't processed it before, and we get more data and more data and more data and more data. And the question is, okay, what do we do with this new data? Should we keep it all? Or maybe even for new data, we can design ways that will enable us to predict what is interesting in this piece of data. And that's what I want to spend the last part of my talk about, really what you do with data on which you know nothing. Okay. So in an optimal way, every time that I get data, I would put a data analyst to look at the data, to do something which is called exploratory data analysis, which is the process really of examining, investigating a given data set. And this data analyst would tell me, okay, this part of the data is more interesting, this is less interesting, these are the queries that are relevant, and then I can use all the previous tools that I've just shown you in order to maintain just the relevant information. The problem is that since we get tons of data, new data all the time, we cannot afford putting analysts on all this information. And therefore, what I'd like to do is to see whether I can do it in some way automatic way. Okay, so before I try to automate things, let's try to say really explicitly what is it that I try to automate. Okay, so first of all, let's try to specify what is exploratory data analysis. Okay, so in general, when a person gets a new data set, what they do is load the data set into some analysis interface, and then they start to do actions. Okay, queries, a sequence of queries. They look at the information that they got, then they perform another query, then they look at the output, they perform another query, and so on and so on. And eventually they decide that okay, they learned enough on the data, and the processing ends. Okay, so what's the goal? The goal is to understand the nature of the data set, discover its properties, estimate its quality, and figure out what may be interesting in it. And there are many modern analysis platforms that help users or data scientists to do that. Okay, so the question that I want to pose now is can we teach a machine to actually do that, to generate a coherent and meaningful sequence of exploratory queries that will show us what's interesting in the data. Okay, the technology that we are using in my group to do that is deep reinforcement learning, which is a technology that works surprisingly well for very difficult tasks. We've been reading in the papers on the Go game where the machine has beaten the experts. It is used for driving cars, to conduct natural language dialogues, and so on. And what we have been trying to do over the last year or two is really try to adopt this technology for finding interesting things in data. So what I'll do in the rest of this talk, I'll do a quick recap for people that are not familiar with the reinforcement learning, to explain what it is. I'll try to explain what from that you would need in order to do exploratory data analysis practically, and I'll talk a little bit about the framework that we designed. If you want to read more about it, there's a paper in Sigmod, and there was another one in Cider at the beginning of this year. Okay, so what is the standard setting for reinforcement learning? So you have an agent, okay, that's the brain, okay? The agent observes some environment, it selects some action to do, and then it gets a reward depending of whether the action was good or not good. Okay, so in a game, you look at the state of the game, you say how to do, and then you get a reward on whether eventually you won or lost the game. And the agent's goal, or what we're trying to teach the agent, okay, automatically, is a good policy for choosing actions so that the mean reward will be maximized. Okay, or you think about it, the cumulative reward throughout the session of the game will be maximized. So let's map that to exploratory data analysis. So again, we have an agent. The agent looks at the data. It issues a query or something like that, and then it gets a reward depending of how good this query was, how much it contributed to understanding the data or finding interesting things. And then again, the goal is to maximize the reward. Okay, so when you want to design a framework that looks like that, there are four things that you need to develop. Okay, first of all, you have to be very specific about the environment, how you describe the states and the action, what is the reward signal, and then you have to choose a neural network architecture to support these things. So let me really very briefly overview what we have proposed as a solution here. So for the environment, okay, what is the environment that we're using? So first of all, you have to understand that the environment, the data that we're playing with, is collection of data sets. Okay, these are the data sets that the agent sees while doing the exploratory analysis, and the actions are actually the user, the query interface. What kind of queries the agent can perform, and then the episode or the sequence of things that the agent is doing is given at the beginning some arbitrary data set, and then it performs a session, a sequence of queries or operations on the data set. So that's the environment. So in order to do that, of course, you know, this is a computer, so you have to represent numerically the data or the state, the display that the user is seeing, and also you have to then represent the action. So let's start with the state. So of course, you need some numerical representation for the data. You cannot just give it a table as is. So what we're using is kind of a compact representation that actually summarizes the important things in the data. So some structural properties of the data, like the value entropy of the different attributes, how many distinct values, how many null values, some information about the aggregates that that have been performed, and also to give the agent some context. We don't just the state that it observes is not just the current display, but also we give it some information about the previous displays, what has been done before. Okay, so this is the state representation. And now, what kind of actions the agent can do? So these are really like parameterized actions. The agent can filter on some attribute with some selection terms. It can group by. It can do back if it got to some display that is not interesting. It can backtrack and so on. So let me point out that for deep reinforcement learning or reinforcement learning in general, having too many actions for the agent to choose from is very bad, because then there is an exploration problem in the learning process. And this is also a problem here, because if you think about it, just for filter, okay, the operation is filter, there are quite a bit of attributes to choose from, and then there are even more terms that you can choose for every attribute. For instance, you want to filter by seller greater than something. This something can be any number. Okay, so the domain of actions is really, really big. So we'll get back to that in a second. Okay, so we discussed the state and action representation. Now let's talk a little bit about the reward that the agent gets when it performs some operation. So in general, the problem is as follows. Okay, the agent performed already, started, and then performed a bunch of operations. And then we need to determine for the next action, okay, what reward should we give it? How do we decide whether the action is good or bad? So in our work, we suggest to use a reward function that actually has three components, which are kind of intuitively what the person would expect from an interesting, from a good exploratory session. So first of all, you want the next display, the display that the agent leads for, would be interesting. Okay, so there are plenty of interesting, formal interestingness measures in the literature that measure the diversity of the information, the conciseness, the peculiarity, things like that. These are all mathematical formulas that can be applied on the data. They give you a number which tells you whether the data is interesting or not. But actually, the challenge is really choosing the right interestingness measure at each point, because there are many different notions of interestingness, and the one that you should choose in a given state may be different. We have a paper in EDBT last year that actually analyzes this situation and kind of gives you a machine learning based approach on how to choose the right interestingness measure at each point of the exploration. So interestingness is one component. Okay, then you also want the things that you see to cover different aspects of the data. So you want the displays that you see through the exploration to be diverse. Okay, so again, we have a notion of diversity that kind of compares the numerical representation of the displays along the way and tries to optimize so that they will be diverse one from the other. And the last thing that you want is you want the operations that the agent performs to make sense. What does it mean to make sense? So for instance, if you explore, if you're a person and you explore a data scientist and you explore a data set and you perform a group by, typically you will not do a group by of more than 5 attributes. Okay, it doesn't make sense to group by 25 attributes. Okay, so you want to teach the agent what a coherent, what a reasonable behavior is, and we do that by semi-supervised learning. I'm not going to go into that right now. You can have a look at the recent Sigmund paper, and all the details are there. Okay, so the point is now we have a reward signal. And the last thing that we have to worry about is the architecture of the neural network. How do we design an architecture that supports these previous components that I mentioned? And again, I don't want to get into all the details. I just want to mention, which something that I already mentioned, that really the biggest challenge in designing an architecture for this kind of network is really the large number of actions. Okay, the fact that you have many actions to choose from, and it's really hard to do good exploration of the space like that. Also, the domain is not completely balanced because, for instance, for the back operation, you just have back. Okay, that's one operation, while for the group operation, you have many types of groups depending on the attributes. And for the filter, you have many more operations because you have a lot of parameters that you can feed to the filter. So there is a challenge in exploring in a balanced way this space. Okay, so I'll just mention that our solution is based on the parameterized softmax with pre-output later. For people that know deep reinforcement learning, this would say something. For others, I'm sure this is very mysterious, but again, have a look at the paper and you'll see what we've been doing. Okay, let me try, before I conclude, let me try to sum up a little bit what I've been discussing and try to give you my perspective, at least, on how to go forward, where I think research should go forward. So I've discussed three things. Okay, first of all, I did some overview of works that have been done in this context, and we've seen there are plenty of relevant tools, but still we're very far from a comprehensive solution, in particular because these tools mainly focused on query evaluation. And we have to extend, we have to explore also all the other domains of angles of or dimensions of the problem, from cleaning, integration, understanding, and so on, all the pipeline of data analysis, and trying to see how we can get rid of data throughout the whole processing. We've been doing a little bit of work using machine learning technology. That's the last part of the talk that I described to you, but again, this is still really at the beginning of this direction. One can support many more analysis actions, design disposal policies that are adaptive based on user interaction. Consider exploration goals, the data exploration goals, which we haven't done in this work. And so on. So I think there is a lot more that one can do in this context, and I hope that I convinced you that this is an interesting area to work on, and you will join forces on that. Before concluding, I want to thank first all the agencies that contributed money to this work, in particular the Israeli Innovation Center, the Binational Science Foundation, the Israeli Science Foundation, and so on. And really, I wouldn't be speaking here to you without the help of all the amazing colleagues and students that have been working with me on this project. There is a list here. I hope I didn't forget anyone, but really, I mean, this is a really nice bunch of people, amazing students, and it has been a pleasure to work with them. Okay, so thank you very much for listening, and I will be available online to answer your questions.